Congratulations, you've made it to the last section of quantitative reasoning. Here we're going to try to tie together a bunch of the stuff we've been looking at and look at a really important concept for statistics, this thing called being normally distributed. What does that mean? And then put the connection between area under a normal curve and percentage and probability, and then make educated guesses using the empirical rule, and finally calculate some z-scores. So this is a pretty important section for anyone wanting to continue on to statistics. And if you're interested in getting a high-paying job with job security, statistics is a really high-demand job. So our author, David Zabecki, went out and gathered these maple leaves, and he measured them. What are these maple leaves? What are these, maple pods? What's he call them here somewhere? Pods, yeah. Some are big and some are small. He measured their lengths, and he created a grouped frequency distribution here, and then he just put in the pods, and it creates this shape that looks like a normal distribution, where most of the lengths are between 50 and 51, and then we have roughly equal amount of lengths as we go further away from that center value. That's essentially the idea of a normal distribution, what it looks like. It turns out there's lots of real-world places where this just seems to show up. When you look at exam scores or like grade distributions, they tend to be normally distributed. Or people talk about them as normal distributed. You could do heights of the average American male is normally distributed, or all American males and all females. You could look at weights being normally distributed. They claim IQ is normally distributed if you agree with how the tests work with things. So it's just kind of a naturally occurring thing out there in the world. So let's make sure we get a basic understanding of it. So suppose a researcher randomly selects 100 adult women, measures their heights, and here's a histogram. Remember what a histogram represents. The y-axis is the frequency, meaning the number of women that are at a height between whatever these two numbers are. So we didn't put a scale here. He did that on purpose. He wants you to think what it might be. And I don't know, should we say the average height of a woman is 5'7" and say that's the middle? And that there's some women that are 6 foot and taller and some women that are 5 foot and shorter, somewhere in there? Maybe. And then if we went and continued to collect more data and got larger and larger sample sizes, we might get a shape that gets closer and closer to this. And the big key concept here for normal distribution is that the mean is the exact center of the distribution, and half of the data values occur above the mean, half occur below, and then they're symmetric as we go in either direction. So let's skip all the way over to page 407, and we'll read this little line here. A probability distribution that plots all of its values in a symmetrical fashion, and most of the results are situated around the probability's mean, is called a normal distribution. Values are equally likely to plot either above or below, that's what I said before, and grouping takes place at values that are close to the mean and then trails off symmetrically away from the mean. In other words, here's what that shape would look like. So if we agree that this is in fact a normal distribution as it appears, and that these are the heights of women in, let's see, I believe this is in inches. Yeah, it's got to be in inches. Then we would say that the mean of the height of women is 63.7 inches, because that's the middle value of our graph. So then we'd say that 50% of the women are above, 50% are below. Well, then we could say, look at the values in between 63.7 and 66 inches, and we could ask ourselves, how many women, or not how many, but what percent of the population of women in America are between 63.7 and 66 inches tall? And the answer is 30.3%, because the area under the normal curve represents the probability that an individual selected has that characteristic, meaning they're between those two heights, Or we can think of it as the percentage of the entire population that's between those two heights is this, when we convert it to a percent. So I guess I should go through his questions here. Number 5 was, what's the mean height? I use mu because we're going to assume this is a population, so all women in the United States. And if you read carefully the words up here, it implies that this is all women. So then if we go to the next page, it says, what percentage of women are between 57.4 inches and 59.1 inches? So going back to our graph, we can see that here is the heights of 57.4 and 59.1. Here's the area. So we would take that area, multiply by 100, and we get the percent of women between those two heights. That's 3.4% of all women are that tall, within that height range. One more question. If there are 31,806 women in the stands for a college football game, how many of them would you expect to be between 63.7 and 66 inches? Well, recall the area between those two numbers was 0.303, meaning 30.3% of all women are between those heights. So if we believe that this sample of 31,806 is representative of the population of America, then we could just take 30.3% of that amount of people in the stands, and we would get how many women we would expect to be within that height. So this is approximately 9573.606. We would use standard rounding things here to get this many women. So now let's connect what we learned about standard deviation a little bit ago. When your data set is normally distributed, we can plot the mean in the center, and then we can run tick marks out away from the mean, equal distance from the mean, and these are called a standard deviation away from the mean. So if we know the standard deviation of the heights of the women, which our author tells us this research suggests that this is what it is, we have a mu of 63.7 and a standard deviation, a sigma, of 2.7, then we can fill in these tick marks by adding 2.7 to 63.7, and this would be one standard deviation above the mean. We could add 2.7 to this number again, and that would be 2 standard deviations above the mean. And then we could subtract going in this direction and be 1 or 2 standard deviations below the mean. We're going to use this mean and standard deviation to then create a normal probability distribution.